There are some 92 chemically distinct kinds of atoms naturally found on Earth. They're called the elements. Here we've represented all 92 of them. At room temperature, many of them are solids, a few are gases, and 2 of them, bromine and mercury, are liquids. Modern physics and chemistry have reduced the complexity of the sensible world to an astonishing simplicity. 3 units put together in different patterns make essentially everything. A proton has a positive electrical charge. A neutron is electrically neutral, and an electron an equal negative electrical charge. Since every atom is electrically neutral, the number of protons in the nucleus must equal the number of electrons far away in the electron cloud. The protons and neutrons together make up the nucleus of the atom. If you're an atom and you have just 1 proton, you're hydrogen. 2 protons, helium, 3 lithium, and so on, all the way to 92 protons, in which case your name is uranium.
For any given element, the number of protons must remain the same, but the number of neutrons may vary. The atomic weight of an atom is the number of protons plus the number of neutrons. Natural uranium may contain 142, 143, or 146 neutrons. That means uranium has 3 natural isotopes, U-234, U-235, and U-238. Some elements, such as tin, have a great number of natural isotopes. Others, such as aluminum, have only 1 isotope. Most isotopes are stable. They would never spontaneously change their atomic structure. But some isotopes are constantly changing. They're busy being radioactive. Given enough time, this radium-88 isotope will shed energy and change. This is how isotopes in the Earth itself emit radiation. The Geiger counter detects their presence. A cloud chamber makes these rays visible to the naked eye. Each new vapor trail shows that another atom has thrown off a fragment from its nucleus. Each atom does this only once before becoming a different isotope. This activity appears to go on almost endlessly. That's because there's billions and billions of atoms in that tiny sample. These mousetraps represent atoms that are radioactive. Every once in a while, a mousetrap's spring breaks down and snaps shut. A tiny bit of mass is converted into energy as an atom changes spontaneously into a lighter isotope. Knowing that some atoms could spontaneously change, in 1939, scientists tried firing a neutron into the nucleus of a uranium atom, the heaviest and least stable atom found in nature. Instead of a minor change from one isotope into another, the uranium atom split into 2 parts. These 2 parts were lighter than the original uranium atom. The missing mass was converted into energy. Also released were 2 neutrons. 1 free neutron has become 2 free neutrons.
Now we have 2 neutrons. This implied a nuclear chain reaction in uranium.
Obviously, that's not what we want to do in reactors. Most reactors are completely incapable of sustaining that kind of neutron multiplication, but it is nevertheless something that takes place in a weapon. Now, I also think that this notion of a chain reaction has perhaps been used a number of times to perhaps scare people about how nuclear fission reactions really take place in a reactor, as if they are an uncontrolled expansion of the number of fission events. That's not really what happens in a reactor, because you reach a point where only one fission is causing another fission, and that is the notion of criticality. It's a state of balance neutronic balance. But early in the startup of a nuclear reactor, you have supercriticality, which is where one fission is causing more than one fission. That's still relevant. But typically, supercriticality in a nuclear reactor is a very, very low number, a number very, very close to 1. It would be like 1.0000 something. Both subcriticality and supercriticality are normal operating states in a reactor. When you want to bring a reactor up to power, you bring it to supercriticality to a certain level. You go up till you get to where you want to be, and then you level out at criticality. And one of the things I had wondered about for the longest time was it seems like this is such a precise balance. How would it be possible in an engineered machine to attain such an absolute perfect situation of balance where you weren't leading to more or less fissions, but you could actually hold at exactly 1.0000, 10 zeros beyond that state of criticality. And what I found to my great interest was the reactor will do it for you if you design it properly.